Hello. So I've only got one more little module for the how concentration depends on time, and it's not going to be that long. And then I'll post some stuff about exercises you can do after you study this set of modules. So it's going to be module 6 to 9. Okay, then there'll be one more set, and then we'll be done with kinetics. Okay, so I'm gonna move on to the OneNote. Okay, so I'm gonna work on the half-life formula for a first-order reaction. But first of all, I want to review a little bit that if you plotted the concentration for time versus time for a first-order reaction, it would definitely not be linear. Remember, it's linear if you plot the log of A versus time. So, but I want to show you on this graph what's meant by half-life. So let's suppose you start at the initial concentration A0, okay, A being the reactant. So we're talking about A goes to products, and the rate is K times the concentration of A. And the concentration, of course, is going to decrease with time. So here is what it is initially, okay? So this is the concentration over time. And when it gets down to half, so this is it's about half of is about here. So this, the time it takes for the concentration, so let's say we started with this concentration, and this is about half of it. Well, it's not a very good drawing, but you'll have to imagine with me. So this is half the half-life that has elapsed. That's what this would be. It would be T1/2. Now, then we have this concentration. Okay, now if we go down to half of that, that's another half-life that has elapsed. So this would actually be 2 T1/2 from the 0. Okay, so every time a half-life passes, you get half, you're down to half the concentration of what you started with. Okay, so so we're going to come up with a formula for that half-life. Now this behavior where where every half-life it drops to half of what the concentration was before. So we're going to analyze this only for a first-order reaction, okay? And so no matter where you are in a first-order reaction, the half-life later, so the number of seconds that equals a half-life, if you wait that long, you will have half of what you started with, no matter where you start. Okay, we'll talk about that more as we go along. So in order to get a formula for the half-life, we start out with this equation that we've used before, which, like I said, is only for first-order reactions. Okay, and so what I'm going to do is subtract the log of A0 from both sides of this equation. So on the left now, I'll have the log of the concentration minus the log of the initial concentration equaling, these are going to cancel, minus KT. So then I'll use the rule of logs, all right? So the log of A minus the log of B is the log of A over B, okay? So this becomes a log of A over A0 is minus KT. And you could leave it like that, or you could realize that, it's another thing with logs, that if you reverse the order in here and make it A0 over A, then you would change the sign. So these equations, both of them, are usable as a starting point for figuring out the half-life. We haven't gotten to that formula yet, so I have to move this equation, this section down a little bit. Because of course it's not doing it because that's what it does. Ah! I'll try it one more time and see if I can do it. Oh, look at that, it worked. Let me get some more room in here. I feel just as silly doing this as I do in class when it doesn't work. But okay. So, so if we have this log of A over A0 is minus KT. And now I say at the half-life. So what does that mean? At the half-life. So in other words, after a time T1/2 has passed. Okay. What is the concentration? Well, it's equal to 1/2 of the initial concentration. Okay, so it's A0 over 2 or 1/2 A0. So at the half-life, T equals T1/2, whatever that is. And the concentration of A is the initial concentration over 2 or 1/2 A0. So, so that means that A over A0 at the half-life would be 1/2 A0 over A0, right? Because at T1/2, so when T is equal to T1/2, when T is equal to T1/2, A is equal to 1/2 A0. So at T1/2, this ratio here becomes 1/2 A0 over A0. So we know that the log of that is minus K, but I'm not going to put T in here because I know that the time when this occurs, when this A, when A is 1/2 A0, so in other words, when I can substitute 1/2 A0 for A, okay, that I know that that happens only at the half-life. So I end up with this equation here, and this is the log of this whole thing, but you could see I have A0 in the numerator and the denominator, so I end up with the natural log of 1/2 is minus K times T1/2. And here's another little clever thing about logs, okay? The natural log of 1/2 is the negative of the natural log of 2. So that's equal to minus K T1/2, and now I can cancel. Believe me, you don't have to know how these things are derived. You just need to be able to use the formula. Did I do that right? What is the log of 2? I need my calculator. I think it's right. Yeah. So the log of 2 is actually 0.693, and that equals K T1/2. So all of that messiness, which you can just forget now because you don't need to know it, boils down to this one formula. This is the half-life formula. Or you can write it this way. T1/2 equals 0.693 over K. I mean, what could be easier than that, right? Take a number, divide it by the rate constant. Screwed. Let's get this right. Where K is 0.03